Why does a stone resting on the ground stay still, but when lifted to a height, it suddenly has the potential to crash when released? Where does this extra energy come from? In energy filament theory, we don't think of potential energy as a mysterious stockpile stored somewhere else, but instead as something much more direct. Potential energy is simply how far you are from your comfortable position on the field slope map of the energy sea. Let's start with gravity. We've discussed how the tension field creates a tension terrain map for the universe. Where things are pressed tighter and deeper, there are valleys of lower tension. When you place the stone at the bottom of a hill, its position on this slope map is close to the most comfortable basin. However, when you lift it to a higher point, you are moving it from a relatively comfortable tension layer to a more awkward one. This discomfort is what we recognize as gravitational potential energy. Once you let go, the stone slides down the tension slope, and this discomfort is converted into kinetic energy, sound, and heat. There's no need to imagine an invisible gravitational energy being transferred around. It's simply the energy released when the stone returns to a more comfortable position. Now, let's look at springs. The same principle applies, but with a different map. Instead of a tension slope in space, it's a tension slope inside the spring's deformation. The natural length of the spring represents the state where the internal coils are arranged most comfortably, with the most balanced tension distribution. If you compress or stretch the spring, you are forcing the internal structure to move from its comfortable state into a more strained shape. This deformation is like being pushed away from the lowest point of its deformation slope. When you release the spring, it returns to its comfortable position, and this process converts the deformation into vibrations, heat, and kinetic energy. This is what we call elastic potential energy release. Next, consider electric potential energy. Here, the electric field has already created an electric tension map in space, showing which positions are comfortable and which are awkward for a charged particle. When you move a charge against the electric field to a more awkward position, the system stores that electric potential energy. Once you release the charge, it follows the electric field slope back to a more comfortable position, returning the extra energy as electrical current, radiation, or heat. When you look at it this way, potential energy is never a unified warehouse storing energy in one place. Instead, it's a rule for reading different maps of tension. Gravitational potential corresponds to the tension terrain map. Elastic potential corresponds to the deformation slope inside materials. Electric potential corresponds to the tension map of the electric field. Each type of field has its own comfortable basin and awkward slope, and potential energy is simply how far you've been pushed from the lowest point on that map. Once you start thinking in terms of these maps, potential energy stops being an abstract form of energy as seen in textbooks. It becomes a coordinate within the energy sea's various slope spaces. In the next season, we will take another step forward with this understanding. Since potential energy is just the position on the slope, is it possible that force is simply the appearance we perceive when we follow these maps and get pushed along them? Tap follow, share it on New Physics, Clear Universe.